So sorry for the delay, but we checked it earlier, but we just checked it with the connection. So that was the problem. Uh, Find it. So welcome everyone. Thank you for the coming for the lecture, and thanks especially to Max and Patricia for organizing the lecture. I'd also like to thank my wife because I made a big blunder before coming here that it's my anniversary today, and I said yes to Max. So Max wrote to me and I said, oh yes, I'll come. It should be fine and no problem. And probably I didn't check it with my wife first. So, but the promise is a promise. So I'm very glad to be here. And yeah, and I promised her, my wife also, that we'll compensate it some. It won't be compensated, but in some other way. So, so thanks everyone. So the the earlier lecture which Professor Rajamani gave, it was more on how humans behave and how do we look into looking in the different activities, and probably I'll move the same area, but on how machines behave and how complex systems behave. So that's the talk, what I'll be presenting about. Uh, just to give a brief overview of what part I am of the group. I'm part of the Diagnostics and the Prognostics Group at NASA Ames. We are a small team in the Intelligent Systems Division, which looks into developing systems health monitoring for different projects. So we have been looking into both the aerospace domain as well as the space domain. In the aerospace, we mainly are looking into aeronautics part. So aeronautics is the future aviation. What are those going to be? We also looked into, there's a lot of work being done into the current passenger aircrafts or general aviation, what they call about it, and also any of the space or the future missions wherein you have to look into autonomous systems. But these systems over the period of time, they degrade, they have failures, and something on a rover or something which is not close to you it has some issue. How do you overcome that part? Like, do you have to have any human intervention? Because at most of the time, there is always a delay. It's not in real time. There is always a delay. So in that meantime, can the system take its own decisions, and can that system be able to perform at least some basic tasks before any human interventions comes in? So that's the whole area of the division works into, and we are part of that division wherein we give health estimates or system health estimates to the observer or the decision maker. So it can be both. It can be a human in loop as well as an autonomous system. So with that background, let's dig into the work what we have been doing, or the work what I've been mainly focused on. So I'm part of the system-wide safety work, which is a project which is developing innovative data solutions, both for rapid, repeatable access to the transportation system. So the NAS is the National Airspace, and in national airspace, for a long time it was just general aviation, which are the small aircraft and the passenger aircraft. But now, since 2018, the NASA Aeronautics Airspace Operation and Safety Program was formed. And why was this formed? Because in the future, we will be seeing this eVTOL type of vehicles, which are the small, short stop vehicles, which may not be flying at 30,000, but it will be flying at like 10,000 or 15,000 feet above. And these are like the flying taxis, what they call, but these are called the eVTOLs or the VTOLs basically. And what we are trying to do is partner up with both aerospace industry and the government and modernize the impact of safety. So how will that safety be affected? And why that is important? Because though they are doing the short stops, we have to be aware of how the surrounding the NAS is going to perform, because it's not just a single vehicle which is flying, which happens most of the time now. Like you may see one aircraft flying every 2 minutes or 3 minutes. But these eVTOLs, probably they may have like 15 or 20 of them flying per half an hour, which is a very high rate. And that brings into safety, which is more critical in that case. Because the airspace itself becomes a lot of dense, and then operating the vehicles in such dense conditions, it's very much important. Our goal is to explore and discover and understand the impact of safety. So that's the main goal of SWS, and looking into the complexities of the airspace and what we are trying to do. So it's not just looking for the current airspace, but when it's going to expand in the future, we need to look into how these vehicles will be serviced and how they will be operated under these dense conditions. And the overview of the project is to develop and demonstrate these solutions. And every one of us has been developing it in their own manner. So at a very, we started with a very niche areas, and then we have now converged into a bigger area, which we just started in October. The first project started in 2018. So 2018 to 23, 24, we had the first phase. And since 24, October 24, we are in the second phase now. So this is an overview. So we have the current technology challenges. We were a part of the TC2, so which is the in-flight safety prediction for emerging operations. So we were part of that. And then there was work which was done on complex autonomous systems. So that was for safety assurance type of work. And now we are into the TC5, then that's the one in orange, which is basically for the safety demonstration series. So initially it was the research phase, and now we are in a demonstrator phase wherein we will have multiple vehicles which will be flying in that aero space. This works. No, it's my system could not connect it, but that's fine. That's fine. In the earlier phase in the TC2, where we see the in-flight safety prediction, there we had our own vehicle. So we were sensoring all our vehicles with what we knew about. So we could put any of the temperature sensors, voltage, current sensors, IMUs, all this system. But now with the TC5, these are the operator vehicles. So these vehicles may have limited access to how the systems would behave. So we may not say, okay, put this sensor on the vehicle. Probably we may not have access to that. So the next phase is going to be difficult because earlier we had the open space of it was like a lab. Oh, I want to put some sensor here, and we could put it there. But going forward, that would be a difficulty. But we are working on that and how our models would translate or transfer it to these new systems. And also there's a concept which we are calling the ISMS, which is the In-Time Aviation Safety Assurance Management System. So that's the management system which combines all this information together from these different projects. So these different projects, they are working probably like 100 or 150 researchers work on each one of them, and all of us converge to form the ISMS system management system. And then this is the research portfolio what we have. So we saw these TCs. So TC1 was for terminal area. So once the aircraft lands, anything after that is a terminal area. So moment it touches, there is a touchdown. After the touchdown, that's the terminal. So any surface movement of the vehicle right from touchdown till it reaches the boarding gate, that's the area what is covered, and that was a TC1 area. Then it was there was VNV for that because verification and validation. Oh. So there was VNV for commercial operations, which was done. And then we were part of TC2, which I discussed earlier. TC5, TC4 was for complex autonomous system assurance because there is a lot of software associated with that. So that's the reason we need to have safety assurance for that. And that was the group. And TC6 is the commercial operation, but all this work is now going into ISMS. So everyone over the past 4 or 5 years have worked on each one of these parts. And the final one is the ISMS, which is so AAM stands for Advanced Air Mobility, and that's where everyone is transforming into. So that's the NAS, the future NAS work what's going into. As a project, there are a few things what we look into. So improving efficiency of the flight, how do you access the vehicle itself or the airspace, how do you expand the services, explore, discover, and understand the impact of safety, because safety is the biggest concern in the sense because we have humans on board. So anything which has to be connected to safety, the vehicle itself, or wherever they are in the space, in the airspace. So though it's in the aircraft which is flying the NAS or when it touches down. Develop and demonstrate the solutions. So that's what we have been doing. So we first started off with initial work where we tested on our own vehicles, but now demonstrating it in a vehicle, other vehicles also, and also which will be part of the NAS. So these vehicles, when they fly, it's actually like they're flying in a airspace, national airspace. So even they are confined to a very specific airspace, they do have communication with the ATC at some point of time, so that they know that there's a vehicle flying. So how do you communicate that information to the vehicle? And then identify and proactively mitigate risks, because there are always certain risks which are going to be happening. It may be something related to the weather, it may be something related to the airspace itself, it may be something related to the vehicle itself, and those are the different risks which may be happening in time during the operation. So how do you mitigate those, and then look into the different target safety levels for that. So our work, especially in the group, we are more on the vehicle safety part, wherein we look at each uh, aspect of the vehicle health, and that's what I'll preliminary focus on. But it's not limited to the vehicle safety itself, but there is a lot of other areas too. Uh, so this is how the future of aviation is envisioned. So we have the human-centric capabilities, which is currently the work or the way we are going into right now. So it's basically safety and density, and this is the current scenario what we have. So you have human-centric. There is a lot of ATCs, human interface is there, or human interaction is there. The next one is the digitally transformed infrastructure, where it's collaborating with different services, and then there is a lot of IoT and machine learning kind of applications. And then the final one is the one what is probably something in the future is the automation enabled diversity, wherein you have the ATCs itself, they are automated. So you have minimum human intervention in those, and they are have highly complex systems, and they are also scalable. So it's not just to a certain area, but they will be scaled to a larger mass itself. So not just specific to a certain ATCs, but the whole ATC would be with a minimum number of operators on board. So currently we are here, but slowly we are almost touching into this part, wherein the work what we are doing it goes into, and then the last part is basically everything is automated, or at least part of it is being automated. But the idea is to move towards that direction and to minimize the human load as possible, and wherever it can be done. Uh, and as I mentioned, we are when we talk about these type of vehicles, it's not just one participant who is there in the vehicle. So probably when we talk about currently in our case, this is general aviation. So that's the single turbocharged aircraft what we have. These are the commercial aircraft. So this is what exactly what we would be looking into. Uh, in our case, these regional air mobility. So we will be somewhere in this area where we are in lower altitude and urban passengers. So this is where the advanced air mobility type of the eVTOL type of vehicles would be. But it's not limited to that. We would have some regional jets coming in. There will be higher supersonic and high altitude areas also, which are part of the national airspace. So it's a combined complex effort. It's not just one specific entity. Oh, if I say that, oh, I'm just traveling from point A to point B, and then I don't care what's happening everywhere else. That's not how it works, or that's not we cannot be isolated type of operation. It has to be integrated with some kind of thing, because at some point of time you may have a launch system, so probably you may have to clear out space. There could be a high impact. There are some cases where you have airspace which are blocked out because there is the specific passenger or the president is traveling, or some high dignitaries are traveling, then they block out the airspace itself. So in that case, if something is blocks out here, probably you may have to reroute your vehicle, but then can you reroute at that lower altitude? So those are some of the decisions you have to take during that operational period. But this is just giving an overview that, okay, when we talk of airspace, we talk of all these contents on those. And if you look at this, the side on the sidebar, it looks at how they are managed. So some are self-separated traffic. So that means they have onboard systems which can do that. Some are managed by traffic controllers, and then high altitudes are managed by some very specific entities. So your management also keeps on changing. So how do you try to look at the eVTOL or the commercial SUAS type of space, which can be automated in some time? So what are we trying to look into? So more operations, the more the operations we have, the more the risk we have. Whenever there is a new mission which comes in, that brings in a lot of complexities, because any new thing which have to be integrated, that will have complexities for the system itself. And how can you sustain under different constraints the way we are going into transforming, like probably electric mobility, which is coming along. Sorry. Which is coming along. So how can you make sure that those kind of electric vehicles are also part of the system, or they are part or integrated in the system? And the three things what we are looking into is digital transformation, how to change to existing systems and integrate them. AM, which is how do you certify them? Because these new vehicles are there, but if there are new technologies which are coming into the system, how do you certify them? So that's a very important thing. And how do you do automation and autonomy? So you have to automate it, but then how much percentage of that can be autonomous, and how much percentage of that can be human in loop? So there is a pros and cons for that. So how do you control that part? Uh, So we looked at how the system behaves, but then there are a lot of complexities and risk involved in that. And the risk, they are basically depending on different areas. So probably the way I was talking about earlier, that you may be flying on a very dense urban area. So in that case, the probability of probably a failure of the vehicle itself, it may be higher. If it's higher, then the vehicle touching the ground or affecting locals on the ground, that's higher, because these are not high altitude planes. They are flying at 10 to 15,000. So they don't have much span to land the vehicle. So probably if they are rotorcraft, they are not fixed wing vehicles. So they are rotorcraft type of vehicles. Some of them are rotorcraft, some of them are fixed wings, but they don't have enough altitude to take that decision. So do they have to find different vertiports which are close by where they can land the vehicle? So that decision has to be taken in case there is a vehicle issue. Some of them are obstacles, so there could be some obstacles, there could be some weather, and the work what we specifically look into is something like limited vehicle performance or vehicle system failure. So if there is a failure in the system, or the vehicle is not performing as per the its requirement, what decisions have to be taken? And these are decisions taking in and route. So we don't know what's going to happen prior or later on, but these decisions have to be taken in flight, and then that's the update the pilot has to know, and also be communicated to the other vehicles which are there. So for example, if there's a vehicle system failure, and if there are 10 vehicles ahead of me to do a landing, can that vehicle get a priority while the rest of the vehicles can move out, and then the vehicle with some failure can take a priority on landing? Or there could be a very locally available vertiport which can accept that vehicle. So those decisions, and that happens in general aviation also, or in most of the cases. But in these vehicles, since they have very low altitude, we have to take those decisions quite in advance, and that's the reason we work on the something called as fault diagnostics area, wherein we try to mitigate the faults, or at least detect faults well in advance, and then predict that how much farther can I go. Like if my battery is low, or that's one of the examples I've been working on. So if my battery is probably has some issues, and I have only 15 minutes of time left for flying. So do I find those vertiports which are closest to me where I can land the vehicle? Or if it's going to last for just 10 minutes, what is the closest airport I need to fly? And then take that decision and land the vehicle as safely as possible. So those kind of decisions have to be taken based on what is my health condition. So it's a health estimate. So Professor Rajamani said about estimator. So we exactly work on that health estimates, wherein we try to estimate the health of the vehicle, and then try to mitigate those faults down the line, saying that, okay, what decisions I need to take, like of the 10 airports or the vertiports I have, I can choose only one or two and then just land the vehicle there. But then there are some other complexities also. You have interferences which are coming. You have some terrain collision because there could be some high mountain tops or something. There is a lot of the work would be based on GPS because navigation systems, but there is a lot of not many times these may be affected by GPS degradation, and we have been working. So these are more or less the topics what we have been working on, the based on the complexities, but applying to a same concept of UAVs or the US type of vehicles. So with that background, we'll move into that was the back end of why we are doing this. But now with this, how do we integrate that as part of our TC2 work or the TC2 deliverable, what we did? So we had an initial ISMS test architecture, and what you look at this are the different service providers. So we talked about that different vehicles are coming in and out. So each vehicle or each service provider may provide a different expertise. So some can provide like dynamic density, some can provide the battery prognostics work. There are some work on the PTT, which is basically estimating the distance from any closest high-rise buildings or high terrains, which is what we talked about. Some can do into the RF part or the density part. So RGSM, the EOSN is basically it's giving an estimate of how much is the density of the population in the ground. So that way I can have my trajectory moved away from it. So I don't, if there is a school or there is some big assembly which is happening, or there is probably a concert happening in downtown, probably I need not take that vehicle from that route. I need to reroute it through some other way. So those kind of actions can be taken. So these are the different service providers, and they are putting all that information on a single bus. So that's the data bus what we have. And then at the bottom, if you see there are other operators or other users who can take that information and then provide it to the vehicle system itself. So you can have log events, you can have some of the ground station operations. So those operations can then go back and forth, and then based on which the operator can take a decision, should I follow this specific route or should I change my route based on my vehicle health itself, and also all the other information what is available through these different providers. So as a till now, we have almost 6 universities which are collaborating on this work, 6 to 7 universities, and we have 3 private operators who actually were providing their data. And in that, when they provide their data, they are also limited. So probably at some point of time, they will not give any information on what my actual sensing information is there. So they'll just give me data at every probably 1 minute update or something. So how do you work on that information? Some of the operators may say, okay, probably no information from our vehicle is given, only you will get some voltage currents and from the batteries, and probably you operate with that. So everyone provides different information, but everything is gathered together and to give you a specific output for how the total health of the total health as well as the system health is going to behave in the future. So that's what we try to look into. And these are something like sockets, basically like software sockets. You develop your own algorithm and then you just connect it to the bus, and the information flows. And once it flows, it is provided to everyone. Then everyone has access to that information, and you can take whatever information is you required for your decision making, and then you can take that decision. So at the lower end, you can have several operators, not just one vehicle, but multiple vehicles around there. I did talk about when you have to take a decision. So in the prognostics case, what happens is whenever I get to know that yes, something is going to fail in probably 1 hour, probably a human intervention is a good way to do it, because humans can think about it and then take a decision on that. But if something is going to fail at a millisecond or second level or probably a couple of minutes, a human intervention would not be an appropriate way. And in that case, probably autonomy would be a better way to take over that. But in case of a couple of minutes or a couple of hours, then it could be pilots and air traffic controls. And anything beyond that is probably like a maintenance. So if I think that, oh, my motors are not behaving properly, or my battery needs to be changed over the period of time, so probably in that case, that is something of a maintenance thing, but my prognostic horizon can give that estimate to me. So I know that when I'm flying my vehicle, that yes, I know there is something the vehicle, the battery pack is probably aging or they are degrading, but I cannot change them right now. I can change them in the probably in the next 10 flight or in the next flight, 5 flights. So that is the kind of information our algorithms give to the operators, and then they can take decisions based on that information. So it's uh, uh, whether it's maintenance or whether it's taking a decision to change the route, so which would happen like closely in couple of within a minutes or 20 minutes. But anything beyond that is called as like maintenance or predictive maintenance. That's what we call. So we combine two of that, both this information together, and depending on that, the operator can take the decisions what has to be done. I'll go in the basic framework of how these operate, and the very good part about this is like I thought I'll like take a story and then go in the depth so that you have a good background of what work we are doing and how it integrates with the actual system. So I went the other way around. So this is going in the depth now, that how the algorithms operate. But to show it is basically you have a system which receives as input. So it could be any system. Uh, Once your system deviates from its actual operation, you identify that active damage progression or what damage mechanisms are there. Once it's detected that there's a problem, then we try to estimate what is the current state and the parameters. So it's basically your state estimation that, okay, there's a fault, but what's the fault magnitude? What type of fault it is? So we try to detect that. So that's fault detection. And then based on that, we then try to make a prediction. So it's very similar to you go to a doctor, you I have a cough, so probably the doctor will diagnose that, okay, why did the cough come from? You did you eat something specific, or did you have cold or something, anything else? And then the prognosis is, okay, take this medicine, you will get better in like 3 days, 5 days. So systems are exactly that way, that you have inputs, something deviates around it, you try to detect that, and that's the diagnosis part. And then you try to estimate, saying that, okay, do I need to take one tablet, or I need to take half tablet, quarter tablet, whatever that is. You estimate that the magnitude, and then you predict that, okay, based on that prediction, your system will fail in probably 2 hours or 5 hours or 10 hours, whatever that timeline is. So this is the whole process. The whole framework is based on this architecture, and we have been working on this and improving as we go forward. And once we know that, when we have to know about the system, the best way is always to go to the first principles, and that's what we have been, the group has been looking into. There is lot of work done on data-driven methods. There is a lot of work on machine learning, and we are catching up. We are also catching up with that part, wherein we are trying to combine machine learning approaches, and I'll talk about that. But the underlying thing, what we are trying to look into is looking into the underlying physics of those systems and subsystems, model those. So try to model the damage progression, what's happening. So if I know if something is breaking, if you take a motor, so motor has like windings, it has rotors. So what is the problem? So where is the problem? So you try to look into the damage propagation mechanisms, determine the threshold. Everyone has a different threshold because each system is different. So they will have different threshold values. So if I take a battery, probably my state of charge is the one which determines the threshold. If I take a motor, probably the internal resistance or the winding resistance is probably determining threshold, or probably the RPM speed. We can set those kind of things. So everyone has a different threshold values. And once you develop those thresholds, determine those thresholds, then you develop algorithms which will propagate them forward. Because my system is moving forward, I know what my current state of health is, but now what I have to do is use that model, estimate my current health state, and predict that, okay, what's going to happen in the next 1 hour, or what's going to happen in the next 15 days. So that is where the model comes into picture. So till the state estimation, it's as we were talking with Professor Rajamani, we use the same thing. We use carbon filters, UKS, particle filters. That's exactly what we use. But anything beyond that is completely depending on the model. So there's no feedback for that. So the model has to propagate. So it's a Monte Carlo simulation from there, but it all depends on how good your model is. So if your model is good, your estimates are good in the future. If your model is bad, probably you are not able to estimate. And the good part, the worst part about this is like, how good is my estimate? If I say something is going to fail in 2 hours plus or minus 2 hours, then that's very rubbish information. But if a model is good and if I say, okay, 2 hours plus or minus 5 minutes, yes, that's a better information because then I have a confidence that yes, whatever the estimates I'm giving in the future, those are good enough. So that all depends on how good your model is. So how good your model developed is, or it can be anything. It can be a first principles models, can be a differential model depending on what you develop around it. Uh, so for as well as I was talking that we looked into the physics part of the model. So for a long time we looked into the physics parts, developing differential equations. So we looked into models for batteries. We looked into some how rotors are behaving or what the wind thrusts are. We looked into a lot of structural modeling. So we do a lot of SHM type of structural health monitoring. So that's some of the work we have worked on composites, wherein we can determine what the fatigue crack growth is. So everyone must be aware of the Paris growth model. Like, okay, you have a crack, but now based on that crack, how will it propagate forward? And then can I determine when it's going to fail? So that's used for bridges, steel, metals. But then we try to work on composites. So that was some of the work what we have done. But now there is also the other side of it is like there is a lot of work done on machine learning. So you have a lot of data available. That data is because IoT is coming up and you just keep on collecting data, so you can develop a lot of machine learning models. But at times what happens is your system, the data what you get from these models is always constrained to a very nominal operation because failure operations are very rare. So if you operate the system for like 10,000 hours, probably you may get like not even a half an hour of failure data out of it because most of the time it's operating normally. Only there are some abnormalities which are captured, and that is difficult to do it. So you need to have a very good data if you want to build good models, especially for complex systems. So what we came up with was a method in where we could combine the two of them. So we combined the physics part of it and the data driven part, and we try to come up with this new methodology, and which is very much coming up now, is called the physics informed neural net. So it's basically trying to learn some of the parameters, keeping your physics model consistent, but using the data to update your models. And you try to check on what the degradation models were. So in the previous slide, we looked at what learn the degradation models or specify what the degradation models are. So we try to use this physics informed neural net approach wherein we could combine the two of them together. And since most of there is PyTorch, there is a TensorFlow, so these are the new Python packages what are available. So this is a new work what we developed wherein we combine the two and apply it to a few of the examples. So I'll just talk about those. So yeah, so this was the earlier part, and I'll just go into a step into diagnostics, how we do it. Yeah, so uh, for the diagnostics part, what we talked about in the architecture, we talked about diagnostics. So what we did was we looked into in the FMEA part. FMEA is basically looking into the root cause analysis. So that root cause analysis was applied to a UAV type of vehicle again. So that's because that's some of the work what we have been doing. But then everyone has their own root cause, right? If you have an avionics system, that would have failed differently. The structures may fail differently, the actuators may fail differently, and the powertrain itself may fail in a different way. So we looked at all those different root causes and how that would affect the vehicles, because these are all part of the vehicle. So each one has a different root cause, and we looked into that. We implemented a Bayesian architecture. So Bayesian architecture is basically probabilistic detection, wherein we able to detect a fault in the system. So the root cause are the top lines. So the root causes are basically the operational conditions, but the lower ones, what you see, the TB, IB, those are temperature, the current, voltages on the each one of the systems. So this was for a power system. So this was the power system what we took mode, and we used one arm of the UAV, and where we were trying to look into that. Is there the blue ones are all battery faults? So in a power system, you have battery, you have the speed controllers, and the motor. So these are the three key structures or the three components. So we looked at each subsystem, and then based on what we observed on the sensors, we were trying to do a Bayesian analysis and then say, okay, which fault it is? So is it a fault in a battery? Is it a fault in the motor, or is it a motor fault in one of the speed controllers? So we just did a basic uh, study, or at least a example wherein we're trying to compute what are the conditional probabilities. So if VB voltage from the battery, voltage from the speed controller, and voltage from the motor is high, that means there is a fault on all three of that. So we did the underlying Bayesian framework is able to detect that, okay, yes, there could be fault in either one of these. So then it ranks it. So it ranks it based on what I think is maybe the highest probable cause. And how is that done? So the probability distributions are based on what the FMEA model, what we looked at. Uh, so we define the probability of causes based on the distribution, based on what will be the cause of these faults, and then applied that distribution to the whole network. And then based on that, it's able to rank it and then say, okay, yes, you see the fault in all three sensors, but the actual fault is in the battery fault. That's the reason the VB has the highest probability. So that's the one which is at the top. So that's because the state of charge of the battery is going low, because you are operating the battery, and that's the reason you see the voltage going down. So once you detect that fault, now you know that, okay, this is the fault. And then you apply the prognostics to it that, okay, I know that the SOC is decreasing. Now how much time do I have before this SOC reaches the specific threshold? So then the prognostic step starts. And that's where so you detect the fault, and then you have prognostics, wherein then you try to estimate that, okay, how much, now I know that the state of charge is the one which is changing. How much time do I have before it reaches the threshold down the line? And here we use the physics informed neural net framework, what we talked about. So we have the system input. So this is the same architecture what we showed earlier, but now we have a physics informed recurring neural net, which we have a system model, which has both the system model, the physics model, as well as a data-driven model. And then that is updating at each step. And at this point, what you see is at the lower point, this is the differential equation. So this is the purely differential equation model, so which is the called the electrochemistry model for the battery, what we have been doing, we developed in the lab. So this was with a few of my colleagues, what we developed a couple of years back. But the unknown parameters in this case are the internal resistance of the battery and the capacity of the battery. So those are the two parameters which keep on changing over the period of time. So the model in our case, what it does is it looks at the input current. So what is my input current? And then based on the whole model, it's able to estimate what this R and Q max values are over the period of time. And then those will change. So the rest of the model is a purely physics model, but only these two parameters are learned using a multi-layer architecture of the neural net. So the neural net only learns these two parameters which keep on changing. So the R max and the Q max, those are the ones which change over the period of time because they age, the capacity of the battery keeps on decreasing. So the equations, the rest of the equations remaining same, these two change. And so we are able to make a prediction that, okay, based on the current drawn, how the R and Q max values are changing over the period of time or how they are decreasing. And we demonstrate that through some of the work what we did in the lab. So in the top, what you see, these are the voltages. So this voltage is basically the state of charge. So whenever you draw current from the battery, the battery is going to discharge, and it has a very specific curve. So that's the curve what you see. So this curve is for a constant current. So if you draw 1 amp or 2 amps out of it, you would see the current constantly decreasing, which is a normal operation. But that doesn't happen when you are actually operating a vehicle. Like when you're operating a UAV or something, you would not see a constant current drawn at all times. So it would be a random discharge because you will take off, you will do some cruise, you will change altitudes, and then you will land the vehicle. And then this is what it would happen actually. Like you are taking off, that at takeoff, your current is very high, so that's why the voltage drops suddenly. So there's a high drop in voltage. Again, whenever you change altitudes, you see the voltage dropping again. And then when you change altitude, like when you are at a lower speed or something, that's when the current is low, so the voltage will jump back again. So it depends on how the trajectory of the vehicle is. But what we try to show this is that the black one is the measurement. So all the black is actual sensor measurement. The blue is the observation only, observations only with single the model or the just the physics model, and then the observations what we see are with the fleet prior. So fleet prior was that we were able to get information not just from a single battery, but from if we had 8 batteries in this case, so we were combining all the information together. So this was that's where the neural net comes in. That I just do not look at what my system is looking at, but if I have a fleet of UAVs or fleet of batteries, each battery may have been seen different changes because the current drawn is different. Some may have done short flights, some may have done long flights, but they age in a different way. So we are trying to gather all that information and then trying to see how can we use that information for my next flight. Because if I if I do flights A to B, A to C, and C to D, probably I have that information available with me. So if I'm doing my next flight from A to D, I need to get an estimate that how good my estimator would be. It's saying that, okay, if I'm flying from A to D, will my battery be good enough to take me there, or do I need to do anything else, or do I need not take this specific route? Probably I have to take a shorter route or something. So those kind of decisions these algorithms give you. And the first part, what you see, it is when I have only information for the in the early stages. So that's my variations are very large. So if you see, there is a lot of variations because there is very less information available of the battery itself. We had 8 batteries, but we didn't know, we were not able to estimate it very accurately. But as more and more information was available, so this was at like 1 kilowatt of total energy drawn from the batteries. This was at 2.5 kilowatt of energy drawn from the batteries, and then this was close to 5 kilowatt of energy drawn from the batteries. So in somewhere around that, we were able to make very less uncertainty. So these are the uncertainty bounds, like how certain or how confident I am on my estimates. So earlier estimates to give an estimate. So these are all predictions. So these are predictions till so if I start making a prediction at 0, probably till 2000 seconds, how my predictions are going to happen. So as I go forward, my predictions were getting very uncertain because in the early stages, but as we got more information of the system itself and the batteries, our estimates were very close. So our uncertainty bounds were very cut down, or at least we were confident enough that we are making good estimates. So this is just to give an idea that how we are able to combine different methods, both from the diagnostics point, like you, and how the framework works. Like you take a system, you see, you detect a fault in that system, and then apply your methods to it, and uh, try to estimate that, okay, what is the health of that system going to be. And why this is important now, that if I know this information well in advance, that okay, my vehicle is going, I'm very certain that 95% confident that yes, the battery will reach that SOC in 20 minutes. The operator is very confident and they can take a decision that yes, I need to land the vehicle now. It's not like, oh, I can make 1 minute more or 2 minutes more. So it's not a guessing game anymore. You are very confident on that, like yes, you have to land the vehicle at that point of time. And we have demonstrated this on small vehicles a lot. We almost did 100 flights, demonstrated that both on fixed wing vehicles and rotor crafts. And the work is continued. So we are still working on it and improving our algorithms. But looking ahead, what we are trying to do is not just apply it to a single vehicle. So I showed an example for the batteries because that's some of the work, my core area of work, what I've been doing. But I've been working on other areas also, like the powertrain of the system. But how can you apply that to weather? Can you predict the weather well in advance? Because these vehicles fly at lower altitude, so the weather is very changing. It's not like the weather at 30,000 feet, but this weather is like at 10,000 feet because it gets affected locally also. So can we use some kind of this physics informed neural net approach to make some predictions? So there are a couple of my colleagues who are working on the weather prediction part. If there is something on the vehicle performance, so can you change the vehicle limited performance? So can you improve the performance of the vehicle at least to make that trip, or to make sure that you are confident that the vehicle will make it to the trip. Any of the traffic collisions. So if you want to, something happens that if there is an issue, can you change the path? Because, but if the path changes, then there are other vehicles which are also moving around. So can you determine that, or can you exchange that information on the bus with other vehicles, so that your change in path may not affect, because probably at this point of time you thought that, oh, vehicle is having some issues, I need to change my path. So if you are going, or going in some other direction, other vehicles may be coming in and they may have some emergency. So how do you exchange that information and come up with a better estimate of the trajectory planning? So that's the another additional work what we are also looking into. So this is just an overview of our work, and we try to demonstrate how we are trying to demonstrate it, and then trying to make sure that we the next eVTOLs, or the phase of the next generation vehicles can be safe in the airspace. In that, I think we have also been very open on the open sourcing our data. So all the experiments what we do in the lab, they're all open source for researchers to work on, develop their own models, compare it with our models. Probably we are not, we don't claim that we do the best models, but there are so many other work researchers who come up and they say, oh yes, probably your accuracy is 92%, we are 95%, and we are like, yeah, that's completely fine, because things keep on moving. There are new methods coming up, and new technologies, ways in which people apply, or researchers apply their algorithms to. But we always open source our data sets, and everyone is able to use this. So we have done on that batteries, we have done on capacitors, MOSFETs, any of the all the electronic systems what we have worked on. So there's a turbofan engine. So we worked on turbofans also for the jet engine. So we had a big simulation for that. We have open source that data set also. So it's a good way for us to share that information with the rest of the research community. So yeah, with that, I thank you so much for your opportunity, and I'm happy to answer any questions.
So you were talking about events, weather events, things that might create a scenario which you have to predict the outcome of.
Yes.
The one that came to mind was encountering a flock of geese on takeoff and
Yes.
Deciding whether you could return to the airport or whether you had to land in the Hudson.
Yes, so we also looked at the weather patterns or migratory behavior of the birds. So that is very much part of the system, wherein if there is a migratory period going on, then how can you predict that there could be some birds which are flying or across, and can you then change the way you take off or land the vehicle, so they can be landed in a very different pattern in that case. So yes, that's a part of the model. Yes. Yes.
You mentioned that anybody in the airspace can add information to the bus, right? The information bus.
Yes.
Is there some way of preventing bad actors from putting
Yes.
false data?
Yeah. So that's a big thing. So there is a work going on how do you identify yourself as part of sharing the information, and who can also gain that information. So bad actors are going to be part of it. So there is a security part team which actually works on. So a couple of my software developers who actually make sure that you identify the vehicle, and then once that vehicle is identified, which is part of the specific airspace, then only that information is transferred to them. Yes.
Do you imagine some of the quality estimation that you're doing would be a requirement on, say, a commercial quad rotor when it's doing deliveries in dense areas, or?
Yes, yeah. So there should be at least prior to flight. So some of the times what we do is when you take off, we do a check on the vehicle itself. So there is a requirement that if when the vehicle lands to its delivery point, or wherever that point is, it should have probably 30% state of charge available. So they do a simulation of that, and we do that on our vehicles also, that okay, I know my vehicle is there, but based on what weight I'm carrying, what is the actual weight of the vehicle, we do a simulation prior to the flight. And if the vehicle at the end of the flight, the trajectory, it says like probably you are at 20%, then the vehicle is not allowed to fly. or it has to change the trajectory to make sure that it reaches with a sufficient fuel. So it's exactly similar to when you fly a commercial vehicle, aircraft. Before it lands, it has to have minimum 45 minutes of fuel left at any point of time, because in case of a go around or any other emergency, it can land to a next vertiport or airport. So it's very similar to that we are trying to implement on these vehicles.
Okay, so that's future though, it's not currently in place.
So currently it's only on our test vehicles what we do. Yes, yes. So it's on our test vehicles, we 100% do it. So once we go in the TC5, we still have to implement that on them. Yes. Yes.
So somewhat related to the prior question, I think around 10 to 15 years ago, the FAA had a mandate to figure out like certification of UAS in the
Yes.
airspace. And I'm just wondering to what extent your research is kind of like targeted at those UAS specific problems versus, you know, obviously there's obviously the manned, you know, flight that's, we're very concerned about safety for that, but how much of the effort is focused on addressing that growth in the UAS space?
So yeah, so all the work, all the reporting what we have is there is a US guidelines now. So FAA has a US flying guideline which has come out. So everyone has to adhere to those. And from our side, what we do is the work what we do, especially in the case of systems health management, that goes as a requirement to those guidelines. So they follow those guidelines, and even for us also, when we fly, our vehicles are numbered. They have to follow a certain protocol. So every vehicle now flying has a protocol. So they just cannot take up a vehicle and start flying it. So they have to be under certain protocol, tag that exactly like the way of pilot tags or has his notes and everything. We also follow those same guidelines that the vehicle took off at this time, it landed at a specific time, and it was in the airspace for whatever number of time it was. So those guidelines are there, and we adhere to those guidelines in addition to our own safety requirements. Yeah.
Thank you. Can we have a group photo? And then we can.
Okay.
Sorry.
Yeah,